I'm going to kick things off with a Bible verse for you all. In the beginning, God created discrete logarithms. In 1969, a bunch of people working at GCHQ invented secure key agreement, but because they worked for GCHQ, they didn't tell anyone. Then in 1976, Diffie and Hellman also invented it, again, independently, but this time they told everybody. And their protocol was based on what's called the discrete logarithm problem. The next year, a trio, Revest, Shamir, and Adleman invented public key encryption based on a related problem, the integer factorization problem. This is how the discrete logarithm problem works. We say 5 to the power of n equals 3 mod 7. And the question is, how do we calculate n? Now, it turns out this problem is actually very difficult to solve. The integer factorization problem, it looks quite different. Now, numbers can be factorized with arithmetic. And the question is, how do you do this? So for a small number like 33, it's pretty easy. For a really big number, it becomes difficult. Now, it turns out there's a clever way to do this efficiently. So Peter Shaw in 1994 said, well, if I can find what's called a non-trivial square root, so not 1 or minus 1, square root of 1, and we'll call it b, and one of these two values is one of the non-trivial factors of n. So it's not 1, it's not n, it's one of the prime numbers that we're looking for. Turns out that if an element has an order r, then it's quite likely that if you raise it to the power of r over 2, that it will be one of these square roots. So using a quantum computer, we can do what's called a Fourier transform, and that gives us the order in polynomial time, and it has a very, very good chance of solving the factorization problem. If it fails, just run it again. It's an efficient algorithm, not a big deal. So this is really easy to also apply to the discrete logarithm problem, because that's closely related to the order of elements in groups. So if large quantum computers become real and practical, then a lot of crypto systems, RSA, which we already talked about, also Algamel, and the DH key agreement protocol, all of these will be totally broken if this happens. We want to find new problems that stay hard even if quantum computers become a reality. One possible alternative is from a rather arcane field of algebra, and it's not clear immediately why this is useful, but I'll take you through the journey. We believe that the problems we get out of this will be difficult even for a quantum computer. We start with a lattice. What is a lattice? Now, I could tell you it's a discrete additive subgroup of the real numbers, but that's not especially useful. The easiest way to understand a lattice is it's a periodic pattern of points in a grid. So I've got an example of a lattice on the right here. A bunch of points, it's periodic, and they're individual points. So points in such a lattice are vectors. So just like with real numbers, we can add them together, we can do dot products, all of that good stuff. So I've labeled the origin there. I've just picked a point on my diagram and called it the origin point. And all of the others are other points in this lattice. So a really important concept is the idea of a basis. So remember from your linear algebra, a basis is a small set of linearly independent, in other words, they're not collinear, they're not on the same line, linearly independent vectors, and you can add them together in any combination to get any element you like out of the vector space. And lattices have bases in just the same way. Here's one possible basis that I've illustrated on the right. So to give you an idea, here's a little simulation I put together. It's showing you a bunch of different ways that you can represent elements of the lattice as combinations of the basis vectors. So we can see, in different combinations, different multiples of them added together will give you each and every point in this lattice. It's important to remember the lattice is infinitely large. I'm just showing a section of it here. Okay, so a question I could ask is, what is the shortest non-zero vector in this lattice? So if you have a look at the diagram, pretty easy to see it must be this 2, 0. Can't be 1, 2, that's a little bit longer. Now, if I give you this basis, much bigger basis, and I ask you, what is the shortest non-zero vector? Well, you could look at the diagram on the right, but let's say you didn't have this diagram. Generating the diagram yourself from this basis would take a very long time. And it turns out that this problem is quite difficult even for a computer. So the shortest independent vectors problem is one possible replacement for the discrete logarithm and integer factorization problems. And it says, if I give you a basis, give me n linearly independent vectors that are fairly short. They're not exactly the shortest vectors, but they're pretty close. And I'm essentially asking you to give me a short basis, a basis of short vectors. And we believe this is hard even for a quantum computer. So, unfortunately, coming up with practical systems based directly on this problem is not so straightforward, so we're going to take an indirect approach. Now, bear with me here. If you take some matrix, any integer matrix mod p that you like, this actually defines a lattice. It defines all of the vectors orthogonal to this matrix. In other words, if you multiply them by the matrix, you get 0. All of those vectors actually form a lattice. This is related to the kernel of the matrix, if you remember some of your linear algebra. And I've just given a couple of examples. If you choose this particular matrix in Z mod 3, then you can verify yourself that these really are two solutions and they are linearly independent. And that gives you a basis on the right. You can see the red vectors in the basis, and that's going to give you all of the other elements in the lattice if you sum them together. So a practical problem that we will use is something called the short integer solutions. So I've circled a bunch of vectors that are close to the origin, and the short integer solution says, given some matrix, let's take this lattice that you get out of the matrix. And the short integer solutions problem says, give me any short element, anything that's close to the origin. And it turns out that you can reduce this to the shortest independent vectors problem. So this problem is just at least as hard as the shortest independent vectors problem. In particular, it's at least as hard as the worst case. So this problem is hard as long as you can't solve every single lattice. If there's any lattice out there that SIVP is hard in, then this problem is hard, no matter what. That's a really strong result. And we can use this to build a nice hash function, a collision-resistant hash function. So this function that I've defined looks a bit fancy. It's just saying, take a binary vector, multiply it by the matrix. And this function is collision-resistant. It says, well, if I could find a collision, Z prime and Z, then, well, their difference is bound to be short because the inputs are they're binary vectors, so they're quite short vectors, they must be. If I take the difference, then, well, the function's linear, so I'm going to get a 0 answer, and that's going to be a solution to short integer solutions. So because SIS is hard, this function must be collision resistant. And it's shrinking, right? The m power and the n power, m can be a lot bigger. So we get this nice variable length property where the hash function makes the result shorter. Now I'll look at how we can construct signatures using a similar idea. So the idea is the signer, know a short basis of vectors, a matrix of short vectors. I'm going to choose a random matrix A, and my public key is going to be A, and then this T value, which is just multiplying my short matrix by A. So if I multiply a short matrix by a random matrix, I'm not going to get another short matrix. So to sign a message, we use this similar idea to RSA signing. We're going to hash the message, and the key is that we choose a nice trapdoor. We choose Y, which is a short vector, and some technical details. We have to make sure that it doesn't leak any information about the secret key. You can read Lubishevsky's paper about that. So we compute a hash, and we multiply the hash by our short matrix and add our short vector. The result is most likely going to be short. It may not be, but it's quite likely to be, and that's going to be our signature. So to check it, we just check that it really is short, and then we recompute a hash. If you do the algebra, you'll see that the verifying result is the same as the signing result. So a related problem called learning with errors lets you construct a public key crypto system. Now, I'm not going to go through it because it's quite complex, but it's the same idea. If I know a short basis, I can solve the problem. If you don't, you can't. So in conclusion, lattice cryptography gives us a way to construct crypto primitives, hash functions, signature schemes, public key encryption, and a lot more stuff besides. Lattice problems are hard even for quantum computers. This is the key point, is post-quantum. And they're also quite competitive in terms of performance, practical performance. They feature strongly in the latest round of American standardization for post-quantum crypto. Thanks for listening. Have a nice day.